Okay, well, welcome to Phoenix here in Leicester. We have a nice crowd in the room, maybe 20 or so people, and we have 8 online. And as I mentioned, I will be recording this. It is being recorded and will go online on the Computer Arts Society YouTube channel. So tonight's talk is entitled Demystifying Quantum Computing, or Quantum Computing Art in particular. I think we all need a bit of demystifying because I'm sure we've all heard about quantum computing. And from what we've heard, it oscillates between the amazing and the mystical, and sometimes more mystical than amazing. And I'm personally really excited to understand a bit more, not just about what it is. And I think one of our speakers in particular is an expert in the mechanics of quantum computing, Jonathan Knoblauch. Hopefully I've pronounced that correctly. But also its creative use. Now, both of our speakers, Ernest Edmonds and Jonathan, have art on show downstairs in the Phoenix Cafe Bar, and you can also see it online. But Ernest in particular has a very long career engaging with technology in his creative process. So I think between the two speakers, we have two slightly different viewpoints that overlap when it comes to generating art with this new technology. So without pre-guessing, but I'm hoping that maybe Jonathan can talk a little bit about the technology and help us with the demystification. Ernest can tell us about how he's identified this technology as something that he can build into his creative practice. And then we will have a little bit of time towards the end of the session where maybe we can ask any of the questions that we might still have about quantum computing. So I'm going to make sure all of my devices are working. Got my Applaud on. Got recording here. I'll let that person in. And to start, I would like to hand over to Jonathan, who is going to begin with an introduction to quantum computing. If that's okay with you, Jonathan.
Yes, thanks. Thank you for the introduction, Sean and Ernest, and thank you all for coming tonight. My name's Jonathan Knoblauch, and I'm calling in from Adelaide, Australia. It's about 5 in the morning, and so I have one of the most interesting day jobs out of most people that I know, and that I get to design and develop electronic hardware that's used in quantum computing. So you'll see the big mess of wires in that picture there. This is the inside of a quantum computer. So that happens to be one of Google's 70 qubit systems. And everything inside there is cooled to millikelvin, so that's colder than space. And all the electronics in the racks around it, that's the stuff that I work on. So I also have a passion for merging technology and art, which is what's brought me here to you tonight in this quantum art exhibition. So I'll start with a brief introduction to quantum computing. So what quantum computing is, why it matters, and where it's going. And I'll put a disclaimer here that I'm not a quantum physicist by any means. So if you have any in-depth questions around that, you can email me or I'll attempt to answer offline. So I'll start with the question. So what if we could solve problems in minutes that would take today's supercomputers thousands of years? So we live in a world built on computing, from the phones in our pockets to global networks. Classical computers have transformed our lives. We've also largely reached the limits of classical computing in terms of being able to model complex systems in a reasonable amount of time. So everything we've invented as humans, we've been able to model in some way. So, for example, aircraft, bridges, computers. It's only through detailed modeling that we have been able to take our inventions from our minds and realize them in our three-dimensional world. And so we've reached a point now where the problems that we're trying to solve are so complex, for example, climate change, that using all of the supercomputing power on Earth combined would take us over 3,000 years to model. So as you can see, we need a different way to do computing. And luckily for our climate, I think we have that in quantum computing. So what is quantum computing? It's basically a different way of doing computing that harnesses the principles of quantum mechanics to solve problems that are practically impossible for classical computers to handle. So if you imagine searching for a lost book in a giant library, to use that analogy, a classical computer is like a very organized librarian who checks every shelf, one book at a time, until the book is found. Quantum computer, on the other hand, is like a magical librarian who can look at every single shelf in the entire library at the same time and find the book instantly. So that's the difference we are talking about in terms of problem-solving potential. So to understand quantum computing, we first need to understand the fundamental difference in how information is stored. So our current computers use bits like a light switch. It's either on, 1, or off, 0. And everything your computer does, from sending an email to rendering a video, is broken down into a series of these 1s and 0s. Quantum computers, on the other hand, use qubits, which are quantum bits. A qubit is a subatomic particle, like an electron or a photon, that can exist in a special state. And then we have superposition, which is our first piece of quantum weirdness. So a qubit can be a 1, 0, or both at the same time until we measure it. So it can be a 0 or any combination, anything in between 0 and 1, so infinite possibilities until we measure it. So it's like a spinning coin that's both heads and tails until it lands. So this superposition property allows a quantum computer to explore many possibilities simultaneously. And the system of multiple qubits can represent all possible combinations of 1s and 0s at once. And then our second, even stranger concept is entanglement. So when 2 or more qubits are entangled, their fates are linked. So no matter how far apart they are, so if you measure 1 and find that it's a 1, you instantly know the other is correlated, is its correlated state. That could be a 0, without measuring it. So Einstein called this spooky action at a distance. So this connection allows quantum computers to perform operations on the entire system of qubits, creating exponentially more processing power than classical computers. So to use another analogy, a classical computer can be thought of like a boat. So a boat can move quickly across the surface of the water, but it is limited to exploring the top layer. So it can't see or interact with what's deep below. And in saying that, it's like a classical computer which can solve problems very quickly, but must follow a specific step-by-step path. So a quantum computer, on the other hand, being a submarine, the submarine can dive and explore the entire ocean from the surface to the bottom and can move in 3 dimensions. So this is like a quantum computer which can use superposition to explore many possibilities at once, and entanglement to find connections between them that are not obvious on the surface. So how do we use this? So a quantum computer doesn't just try all the answers and pick the right one. So instead, algorithms are designed to manipulate the probabilities of all possible answers using quantum interference. So interference is like throwing many stones into a pond. The ripples, which are the probabilities, interact. So we programmed the computer so that the right answers, the probability waves, reinforce each other. So that's constructive interference. And the wrong answers, like the wrong answers waves, cancel each other out. And that's destructive interference. So when we finally measure the qubits, they collapse into the state that has the highest probability. That's the correct answer. Or back to the library analogy, it's like reading every book in the library simultaneously, then picking the right page instantly. So why does it matter? So quantum computers won't replace your laptop for browsing the internet. And so they're a very special purpose machine for specific complex problems. So some of the areas that quantum computing can certainly make a difference are in chemistry and drug discovery. So, so they can simulate molecules to design new medicines faster than trial and error labs. And that's because nature isn't classical, it's quantum. So it's nearly impossible for classical computers to simulate these, and especially with the complexity of today. So quantum computers could accurately model these interactions, leading to new medicines, better batteries, new materials. Climate modeling, which you've mentioned. So current supercomputers would need at least 3,000 years to model climate change accurately. Cryptography, that's a big one. So quantum computers could break the public key encryption like RSA that secures most of our online communication today. But fortunately, scientists are also developing quantum safe encryption. There's also places in finance for optimizing portfolios, risk analysis, fraud detection, and optimization problems where, like global supply chain, where they can solve complex optimization problems more efficiently than anything else. And one of the first examples that I heard of when I first started in quantum was finding a better catalyst for fertilizer production. So that's currently is the cause of 2% of global CO2 emissions. And at the time, that was going to require like what we thought was a relatively small quantum computer, 32 qubits, to try and solve this or simulate that, model that fertilizer catalyst. And the goalposts have moved, but I'll talk a bit more about that in a minute. So quantum computing isn't faster at everything. It's faster at specific problems that classical computers struggle with. So current state and challenges. So, so if they're so great, why don't we have one in every office? So that's because building a quantum computer is incredibly difficult. So there's hardware issues. So qubits are fragile. They lose their quantumness, which is a process called decoherence. They lose that very easily from interactions with their environment. So even tiny vibrations or temperature changes. So they need extreme isolation, often requiring super cold temperatures, which is colder than outer space. Error correction. So this fragility leads to errors. We need complex error correction systems, which in turn require many more physical qubits to create a single, reliable, logical qubit. And so classical computing error rates are down in 10 to the minus 20, whereas quantum error rates start around 1 in every 10,000. And so in order to create more reliable qubits, a logical qubit must be used, which is made up of many qubits, say 100 qubits, to make one logical qubit. So now instead of the catalyst problem being a 32 qubit problem, it's now a 3200 qubit problem. So you're already out by a factor of 100. So another challenging area is algorithmic. So many quantum algorithms are still experimental, but breakthroughs here can really accelerate the timeline when they do happen. But algorithms that can take advantage of the exponential speed up are harder to find than was first thought. So over the years of my time in quantum, at least, it was found that many algorithms that we thought could be used in quantum computing just hadn't been optimized due to developers using faster GPUs or faster CPUs coming along. Instead of making the most efficient algorithm, they just threw more GPUs at the problem. So that moved the goalposts and increased the size of the quantum computer and the size that was needed to achieve an advantage over classical computing. So in terms of the timeline, we're in the early internet stage. So we have exciting prototypes, but we're not yet mainstream. And we're in an era called the noisy intermediate scale quantum era. So companies like Google and IBM have built processors with dozens or hundreds of qubits, but they're still noisy and limited. And there's been some achievement of quantum supremacy for a very specific abstract problem. That was Google's Sycamore processor that performed a calculation in minutes that would have taken a supercomputer thousands of years. So in saying that, practical large-scale applications are still a few years away. So just as a quick summary, so quantum computing isn't just about faster calculations. It's about a fundamentally new way of processing information. So leveraging the very nature of reality at its core. So while practical, world-changing applications aren't quite here yet, the field is advancing rapidly. So we're moving from a scientific curiosity to a technical reality, and it promises to unlock solutions to some of humanity's most complex challenges. So quantum computing is about possibility, solving the unsolvable, seeing the invisible. And while the scale required for a practical quantum computer is still a subject of ongoing research and debate, and as new algorithms and emerging technologies emerge, then they continue to reshape expectations. So nonetheless, the exponential advantages quantum computing promises in targeted applications explain why it is so highly sought after today and in the future. So beyond utility, the beauty of quantum. So quantum mechanics produces hidden imagery. It's this hidden imagery that attracted me to using quantum computing as an art form. So wave functions can look like probability clouds that look like abstract art, interference patterns, double slit experiments, create cosmic light visuals. Entanglement networks can be visualized as glowing webs like constellations or neural pathways. And so quantum computing isn't just about solving problems. It's about seeing reality differently. So whether you're a scientist, an artist, or simply curious, quantum computing invites us to imagine bigger. And the future isn't just about faster machines. It's about expanding the boundaries of human thought. So that was an introduction to quantum. And I'll now move on to some of my artwork. So my quantum artwork for this exhibition explores some of the fundamental imagery that can be produced when tuning spin qubits. So there is a tuning process. So whenever a quantum device is cooled down to millikelvin in a dilution refrigerator, which you saw at the first slide. So the system is basically calibrated to make sure that the quantum device is working properly. And there are many things that can go wrong with this process and with the quantum device itself due to noise, the cooling process, causing a wire to break, or the fragility of the device or the system in general, like impurities in the material. So I've used Python to simulate ideal conditions for a quantum device. And this artwork is indicative of the first time I saw this kind of imagery in a working quantum device. So simulating quantum devices in this way uncovers a hidden beauty within the interactions of subatomic particles that bring about the foundations of quantum processing. Spin qubits are the building blocks of many types of quantum computers, and the artworks reflect the movement of electrons as they are added to or removed from the system. And the color variations illustrate the resulting shifts in energy levels. So this work builds on the first piece and introduces a much larger voltage space for electrons to be added to and removed from. So that is reflected in the increased number of hexagonal transition lines. And the hexagonal lines represent the boundaries of different charge states within the system. Their angles and shapes are influenced by parameters such as the distance between quantum dots and the applied voltage ranges. The contrasting colors in this case help to add to the illusion that the lines are moving as you move your eyes around the image. Quantum dots are the semiconductor boxes that are used to trap single electrons. And spin qubits are also a popular option for highly scalable quantum computing, as they can be produced using existing mature silicon manufacturing industry processes. And for this work, I've incorporated noise into this artwork to show how fragile these systems can be. A quantum device needs to be able to show distinct energy levels in distinct color variations in order for it to be able to be used in future quantum processing. It would be impossible to entangle electrons in the presence of this much noise, and it only takes a tiny amount of noise like this to make the device unusable. And then this artwork was part of an investigation into how artificial intelligence might be used to simulate and model quantum systems. So I iterated over some AI-generated Python simulation techniques, which showed promise, like in this image, but you can see the illusion of movement to the left and right from the middle of the image, but it also illustrated the limitations of AI in this field. So while AI still has a way to go in modeling such complex systems, it can still produce imagery with its own unique beauty. So that concludes my slides, so thank you. And I'll hand you back to Ernest, who will talk about quantum tango.
Okay, thank you, Jonathan. That was great. Quantum Tango is the name of a work of mine, and it's on show. It's on show in the first gallery downstairs, whereas the prints are on show in the cafe area, as you know. I want to say a couple of introductory things before I talk about these prints and whatnot. First of all, I use quantum logic, qubits and whatnot in these recent works. But there's nothing magical or strange about that. And I want to just remind you that the use of mathematics and logic and so on in the arts is very, very old. Here's a couple of quotes from the music world, not exactly recent music. And even in the Mozart's case, using dice, so introducing chance into the algorithm. So, but in the visual arts, most people will have learnt at school about the golden ratio, which has been used in visual art for a very, very, very long time. It's a mathematical device for producing certain kinds of harmony. Perspective, of course, is a widely used mathematical method for generating the structure of many artworks, especially in Renaissance times and after that. More recently, this is a bit of code I was working on, actually, I think 40, 45 years ago, so it's a bit old, but never mind. This is when I started using logic to deal with the structure. It's no different really, it's just another way. The big advantage is I could do it using a computer, which means I could get the computer to do some of the work of using that mathematics, okay? But remember, I was using logic in those days. And one of the ways I used logic was to drive change in time. So I could start to make time-based works that change forever using a computer, the computer running forever, as it were, using rules based in logic to generate the images. And then I could add interaction to that, because I could have like cameras and microphones, analyze the images and analyze the sound as time went on in the room where the artwork was, and use that to change the process that the logic was using in order to generate the images. Well, relatively recently, I mean, in the last 20 years, I've been making a series of works called Cities Tango. And the point about this is that these works exist in many locations at once. In the case of this image here, this work was in two locations. It was on the Expo exhibition in Dubai and in the street in Leicester, okay? And the left-hand image is in Dubai, and there you can see there's an image from Leicester in it. And you can't really make it out very easily here, but in that street scene in Leicester, there is actually an image of the desert near to Dubai. And of course, there's all that colored stuff. These were many layered works using photographs, using live images, and in particular, using an abstract images of the top layer. And those abstract images generated by logic, changing the colors, changing the widths of these stripes and the positions of them, and determining how long each one was shown before the next one came up. All of that done by logic. And as you can see, the color parts were all vertical stripes. Okay. But then recently, I've been making works like this. It's another extension of the same thing. This is a work which actually existed in 3 locations. One was in Vancouver, at the SIGGRAPH exhibition. One was in Baku, one was in Italy, and another one was in London, in an art gallery in London. And you notice that we no longer got vertical stripes. Well, we've not got vertical stripes because the logic that I used to generate this information was quantum logic and used qubits rather than bits. And that introduced a level of uncertainty into the work, which meant that these rectangles were no longer necessarily rectangles. Okay, so by moving from conventional 2-valued logic to quantum logic, I started to generate more varied images and more varied timescales and so on and so forth. So on the left, you see an image from the old Cities Tango, and on the right, an image from the new Cities Tango, using qubits. So just to remind you what Jonathan has already told us about, the bit being 0 or 1, but the qubit being something between 0 and 1 with some kind of probability until you measure it. Okay. And so in this case, the 80% and 20% means it's much more likely to be a 1 than a 0 when you measure it, but it might be a 0. So this is a whole different logic, which is interesting to explore as an artist. The current work, which you can see downstairs, one of the nodes is between Baku, that I mentioned before by mistake, Baku, London, and here. So Leicester is connected to Mayfair and to Baku. And these 2 pictures are pictures from the window of the gallery in London, where the work is displayed. And you can notice that there's a camera on top of the screen. So each of these nodes, I call them, so in each location, there is a node which has a display and a camera. And the computer is analyzing the images coming in from the camera and modifying what happens according to whatever it detects in the images. Okay. And it is running in ways that we don't know how it's going to be. Okay. I have the rules. I know what rules will be obeyed, but not what will happen at any one particular moment, because that partly depends on what's happening at each of the nodes. They talk to one another, and partly depends on what's happening in front of the cameras. There are 3 cameras in this case, of course, which drives the work. So obviously I don't know exactly what's going to happen, but it's not chance, it's quite determined, but it might be, it looks like chance. And this is this current work going along here using this 3-layered approach. So this layer, the first layer is the abstract images generated using quantum logic. This layer, which is a real-time image, that's the street outside the gallery in London, and sometimes photographs, like what you see there, the image you see there is a photograph. So there are 3 layers. And the work continues in this way, changing forever and connecting the different locations to one another, sending these live images from one location to another. And so you can participate in this work. If you go downstairs, there's a screen with a camera there. And if you move around in front of the screen and go and have a look, you might even see a picture of yourself come up. And if you do, you can be sure that someone in the street in Mayfair will see you too. So if you don't want to be seen in Mayfair, if it's against your religion to be seen in somewhere like Mayfair, then be careful what you do downstairs. So I'm using only part of all the stuff that Jonathan has told us about, because I'm new to quantum computing, unlike him. And I've only been working on it for about a year, although I thought about it for rather longer than that, but I've only got round to it more recently. And knowing Jonathan has helped me do that because he's been able to help me with providing the quantum power, if you like, or the power and the simulations to actually put my ideas into practice. So the prints downstairs, so we've each got 10 prints in the show downstairs, are basically stills from the Quantum Tango. My prints are stills from Quantum Tango. And you see here, for example, I'm very interested in colors that are very close together. Like if you see on the left-hand side, if you don't look very carefully, it looks like just one color there, but actually, of course, there are two colors very close together. And this is my interest in the perception of color. My interest in encouraging you, the audience, and me when I look at it, to look carefully at the image, okay? And to see what does it make. If you look on the right-hand side, it's even more difficult to notice, unless you look very carefully, that there are two different colors there. And these colors are generated by the logic, okay? So the hues are chosen by the logic, and the gaps between these colors are influenced by the amount of movement that the camera has detected in front of the image. This was an interesting chance thing that I found when I was in Vancouver, installing the work in the SIGGRAPH art exhibition there. And it was running in London, running 24/7. Of course, there's an 8-hour time difference between London and Vancouver. And images came up because people were walking by or driving by in the street in Mayfair. And we got pictures like this. Well, what is this? Well, the camera is above that screen, but behind a glass window. And so what we see here is an image of the street, and on top of it, an image of the screen that is being showed at that time because it's reflected from the screen on the inside of the window. So this became a very nice chance thing that I discovered something that I could do, which I now, next time, I'm going to make sure I use it deliberately. I'm going to work out how to make use of this nice device. And so I'll just tell you one anecdote, which was I was talking with one of the volunteers who was guiding people around the exhibition in Vancouver. And I mentioned that this was because he wanted to know what to say about it. So I mentioned London. And he said, oh, I really would love to be in London. So I said, well, just come over here. And he came over in front of my work in the Vancouver exhibition. And it wasn't long before I saw a picture of himself in that image in London. So I said, there we are. We got you into London by art. So these images are hopefully abstract. There's another aspect of this which is very strange. The images themselves, the photographic parts, whether they're live or photographs, are not drawn, painted carefully or whatever. They're just taken, and like the live ones, I have no idea what the live image is going to be. It's just whatever's there. So I use them in an abstract way. So you can think that this, so in the logic in the system, in the quantum logic in the system, I just have these colors in a table, and one of them is use a photograph. So I use the photograph as if it's a color. Okay. And so hopefully these works connecting in at the moment 3 cities together. Okay. And that's one task that's being done. Secondly, generating new and unpredictable, nevertheless determined abstract images And thirdly, physically relating you through snapped photographs between the different cities. It's my current experiments in quantum logic. First step for me. So I'm, in terms of the quantum, I'm a long way behind Jonathan, as you can see. But nevertheless, it's another step in a history of work that I have been doing now for a very, very long time. And it's going to be the next few steps. We're going to see more and more like this, not just like using that reflection in the window, but all using more and more quantum logic. Unfortunately, not having artworks driven by quantum computers, I think that's beyond my reach at this time, but using simulations and using the results of quantum logic analysis predetermined. There we are. Sean,
Thank you very much. So we have enough time for some questions, so I will take off the slides so that we can see Jonathan. And Jonathan, are you okay for questions for 20 minutes or so?
Yep, sure.
Great. Okay, I'm sure. Well, I know we have some. I have to try and I have to use my Zoomer because I can't see this screen very well, even though it's my own. Great. So, yeah. So I'll be okay with sharing a screen like that. So, first of all, in order to manage this, I'll direct the first opportunity for questions to people in the room. And if anybody online has any questions, type them in and I will be able to get them from the chat. So anybody in the room have any questions? There was, oh, okay, at the back there.
Logic is very loaded word. My understanding of logic is very different from maybe what you understand. And also, what's the difference between logic and coding? And now that with OpenAI that you can extract a prompt with words and it's type of words into.
I think you both probably have. I know Ernest,
I think.
your PhD was in logic, wasn't it?
Yeah.
Mm.
Yeah, so I actually worked on logic before I worked on computers. Well, actually, computers are logical machines. And the coding is a way of describing how that logic should work, right? So fundamentally, the coding is instructing the computer to use its logic, you might say. However, the coding languages that we have used and do use don't look much like logic mostly. And however, there are some languages, including ones that I myself have used, that do implement logic as a coding language. So that, for example, the famous one that was used during, well, quite a long time ago in this country and around the world then was a language called Prolog, and log standing for this logic, programming in logic. And so you actually wrote logic, which I did quite a lot. That example that I put up as one of my early slides was actually logic written out as code for this language. So if you look at a language like Python, for example, these languages, they are instructions to do things in a particular order, which isn't anything much to do with logic as such. But what happens is the compiler or interpreter, whatever, turns that into something inside the computer, kind of turns it into instructions for the logic to work. Jonathan, do you want to say something?
I didn't actually hear the question. What was the question?
Okay, it was the difference between logic and code.
All right. Yeah, well, I mean, I work as a FPGA engineer by trade, so I work in register transfer logic, and so I deal with hardware-based logic. My job, and so yeah, Ernest was talking about the differences in coding. So I work in digital hardware logic every day, and that can be used in coding as software, or in my case, software that's programmed as hardware.
Great. So do we have another question in the room, and then we'll look at some of these questions online?
Yeah, one over here.
Right.
So, you're saying that colours that you're using in that were determined by the logic, right? And you were saying the images were one of those colours. Were there lots of different images that were? How were you selecting those images, or were they like curated? And I suppose the same with Jonathan, the colours that he was using. I realise you'll have to take this back. But he was using curated as that product of the logic.
Sure. Yeah. So in those works, so as I said, there's the abstract level, and of course there's the real-time level of the image photographs as it were taken at the moment. But then there are these photographs. They're curated, right? And they're either photographs that I've taken, or that someone has taken on my behalf, or kindly taken a set of them, and I've selected from those. So they're selected, either taken or selected by me as part of the artwork. Yeah, so for example, a lot of the images that we see in the current work come from the fact that I was invited to put this work into SIGGRAPH, and the SIGGRAPH, it's a big computer graphics conference that was held in Vancouver this year. It had a theme of relating nature to the human-built environment. And so that drove some of the ideas for what photographs would be appropriate in this. So in this case, you have images like there's images, for example, of a tree growing through a fence and things, etc. Okay.
Okay, so we do have a couple of online questions. The first one from Eduardo. So, Jonathan, do you have any prospect on the application of quantum computing in games?
Having trouble hearing.
So I don't know if that's specifically to regarding computer games or games
Computer
generally.
games. All right, for quantum computing in games, yeah, it's not going to do things like improve like graphics or load time or anything, but it could be used for optimization tasks like procedurally generated levels. You could use it to create truly random numbers. That would be a step up from what they have today. Yeah, I think it's in games that yeah, the generating levels you'll get you'll be able to use more dynamic physics and more immersive VR, I think. But I think it's all very early stages for that sort of stuff.
So I think one thing you said was that you can't imagine us having a quantum computer on every desk because they're for particular types of tasks. And of course, the other area of a lot of innovation in computing is massively parallelism. So we have graphics cards with 16,000 cores that can be used for AI. So maybe do you think there's this sort of dual development? We might have increasingly powerful parallel computers on our desk, but maybe the quantum computer is in a data center just for those tasks that we need to use its particular capabilities for.
Yeah, it's definitely a situation where you'll be using it as like in the cloud or for very specific purposes, and there's a lot of hybrid work going on, combining classical compute or GPU type based work with quantum computers for that very specific like physics modeling or quantum simulation.
And then there's a question from Brian Reffin Smith. I think it would be great to have Brian ask the question himself. Is that okay with you, Brian?
Yeah, can you hear me okay?
Yeah, fine.
Okay, just before I say anything, I at least couldn't hear any of the questions at all. Had to sort of reconstruct the questions from the answers. So when people are in the room and asking stuff, or when you, Sean, are talking from somewhere away from the mic, we actually can't really hear anything. But anyway, perhaps that's a metaphor for some kind of thing going on here. I got sort of two linked questions, one about analogies and the others about practicalities. Both Ernest and Jonathan said that something looks like something. Ernest said about some of the colors that were changing and so on. He said it looks random, but it isn't random. Jonathan said some of these interference patterns, which are, representing states, presumably all at once in a quantum computing situation, look a bit like art. I don't think he said a bit, but look like art. Now, as probably most of you know, when anybody says something looks like art, I get a bit worried. Is it possible that the power, at least in the foreseeable future, let's say my lifetime, another 20 years if I'm really lucky, would be not in the power of quantum computing, but in the analogies that come out of quantum computation. So if I use computers in my work quite a lot, but I don't all that often use the power that I could use in a computer. I do fairly simple things and they give ideas and analogies come spinning off them. So I don't know, Edmund or Jonathan, which of those possibilities or potentialities do you think will be the most important? Using quantum computer, if we ever can, to make art or do something like art, or looking at what's going on with it and then saying, this is like something that I could do with a pencil and paper,
So, Jonathan, how should we do it? I've got a two-part answer. So if you've got a one-part answer, you maybe should go first.
I guess practically wise, I think there could be scope for in the next say 5-ish years to be using commercial quantum computers for art, but it's not really there yet. But yeah, I think it will depend a lot on room temperature quantum computing advances, because that's kind of where because it's practically like the cost factor of quantum computers is obviously astronomical compared to any real scaling so we would want to be, from an artwork point of view, looking at different quantum computers like diamond-based nanodiamonds and systems that don't require like more like a quantum accelerator, so you can use that sort of power to do your different physics modeling and simulation, and take it from that sort of point of view versus a giant, server-side quantum computing system that's many thousands of dollars an hour to use. Ernest?
Okay, thanks. Yeah, so good questions. So maybe I can just take it, as I said, in two parts. First of all, I'll deal with random, and then I'll deal with the art bit. The random thing is really interesting because, in truth, I use random numbers in this latest work, but these are random numbers that are generated from quantum logic, which actually means they're truly random. And I've never used pseudo-random numbers because the pseudo-random numbers aren't random, but they look like random. In fact, they look more random than the real random numbers, because the following sequence can easily be random. 5, 5, 5, 5, 5, 5, 5, 5, 5 is a perfectly reasonable sequence to get if it's in a random number series. But you won't find many pseudo-random number generators that would ever produce that. And in fact, some people, for example, I think Spotify had to change their algorithm from using real random numbers to things that looked more like random numbers because people didn't like getting these kind of repetitions. So on the art side, looking like, I mean, I think this is a deep question and a really important point. And for myself, I think it's the conceptual leaps rather than the physical hardware leaps that are really important. So I've always been interested in computers for computation rather than computer hardware. And the real advances were made in mathematics and in the study of the foundation of mathematics, where the fundamentals of what makes a modern computer possible, I mean the standard computer, were invented. And it's these conceptual leaps that are really interesting. You may or may not, and I often do, use a real computer to help deal with that. But the real point is like the algorithm, if you like, is the conceptual idea, the so-called finitist model, whereby you have an algorithm that can generate an answer. So yes, I think that the future really is in this analogy is dealing with the concepts. I haven't really got my head around the quantum computing concepts enough to deal with that properly yet, because that's the exciting thing to be working on now, in my view. Yes, I think the analogy is more important fundamentally than the actual matter, facts of the matter.
Then we're very lucky, aren't we? Because we don't actually need a quantum computer. We just have to be advanced enough in our understanding of what a quantum computer would be like. And then we can make art analogous to that.
Except that it gets much easier to understand if we do.
If we've got one, okay.
For example, very few people understood the foundations of mathematics and the use of finite methods and logic. And people, for some reason, found logic, although it's actually very simple in a way, very difficult. But once you got it into computers, it became more available and more comprehensible. So I think it does move us on to have the physical thing in terms of our ability to handle the concepts that lie behind it. But yeah, I mean, we don't disagree on this really.
Thank you.
I wonder if I could
Can I just tell you, Sean, that what we just heard was that when you're not here, people can't hear you. So you need to come here.
Yeah, I will. Okay, so a quick follow on from that. Jonathan, do you know, can you hire quantum computer time through AWS or Google or something? So if you want half an hour of quantum computer time, can you buy it now?
Yeah, you can. It's well, I don't know all the pricing, but it's in the order of thousands of dollars an hour. There's some stuff that you can do initially on smaller systems, but yeah, and maybe 5 years ago you could do things sort of much more reasonably priced, but it's sort of turning into a bit more of a commercial venture now versus a research. They've got some things there still for research, but most of it's more for finance companies and that sort of style of computing for modeling various things. But yeah, you can. There's some are better than others. Yeah.
And how would you define a problem to be solved? Is there a programming language, the quantum programming language, or do you define a problem now?
Each company kind of has their own coding sort of development environment and languages that they've developed to deal with the like quantum logic, like either like as like a gate simulation kind of system, something like where you have like a user interface where you can join different logic gates together and make your quantum logic that way, or full APIs and all that, obviously.
So this is for me personally. I couldn't, for example, have a Python program that takes an input, and
yes,
I could. And
yeah, absolutely, yeah, Python.
I could run that 1 million times with different inputs, and it could be done instantly. Is that sort of possible?
Yeah. Python is used extensively. Yeah.
Oh, so there you go, Brian. We could club together and maybe buy 10 minutes of quantum computing time.
Fine, yeah. I think I'm going to put 55555 into the Euro jackpot because it's as likely as anything else.
Well, it is, yeah, true. I have a question that I've been wanting to ask for ages. So are there any other questions before I ask mine? Oh, great. Okay, so my question really is about the interplay between quantum computing and AI. And by interplay, I mean, is AI going to enable us to design better room temperature quantum computers? And will quantum computing allow us to build more complex, comprehensive, faster AIs? Maybe, I'm sure Ernest has an opinion, but maybe start with Jonathan as the developer.
I'm not sure if the current AI can help build quantum, but it might work the other way around. Yeah, like intrinsically the types of problems that quantum could solve and sort of quantum like networking type problems could conceivably help AI development potentially. Yes, but I'm not sure if I don't think AI well, apart from sort of some quantum simulation, it is being used in smaller quantum simulations at the moment for that.
Yeah, I'll just add to that. I agree with Jonathan, but to add to that, if by AI you mean what the popular press calls AI today, then I think it's that way around, that quantum computing can help AI rather than the other way around.
So what I wondered about with the potential of AI, which is prediction and pattern matching machines, not just LLMs or whatever the popular press thinks, are the sorts of problems that you're trying to solve as a quantum computing engineer, the sorts of problems that AI systems might be able, and in the broader sense, might be able to help with?
Not in any more than classical computing can do. Maybe might move the goalposts a little bit, but no, I think it's sort of intrinsically quantum problems, I don't think AI can really do anything much better than, like, it'll be a little bit better, but not really anything that's like you won't get an exponential speed up, for instance, from AI.
So in terms of the, I don't know what the industry expects and the development, but are developments in quantum computing measured in how many qubits you have? Is that
Yeah.
Yeah. So what is your prediction currently with how how exponentially the number of qubits might increase?
Well, I guess well, it's been, I guess, 10 years away for 40 years, but the it would be in the million. For something to be a practical quantum computer that can solve the types of problems that we have limitations on now, it's in the millions of qubits, and we're in the hundreds at the moment. So it's probably still 5 to 10 years away. Probably towards the 10 years away for something that powerful.
Okay, well, that's interesting. So it's been a long journey, isn't it? A long journey to develop the technology. Yeah.
Yeah.
I think there was a question.
Oh, sorry, was there? Oh, sorry, back there.
So this is related to this question, really. I was wondering what the bottlenecks are in quantum computing, in the same way in classical computing, you need to make sure.
Okay, so I'm going to pass that on just in case people can't hear. It's really a question about what are the bottlenecks in quantum computing. I guess it's that same thing. What are the problems that are stopping you having a million qubits?
Problems with having a million qubits? There's a lot of problems with a million qubits. So every single one of those qubits has to be controlled really intricately, and so you have to be able to measure the qubit and also move it around. So because it might be an electron that you're trying to manipulate in like its 3D space. So you have to be able to do that with a very, very low error rate. And so realistically, this million qubits is going to be, there'll be some number, say 100 qubits to make one of these logical qubits. So that will be something that's protected from a lot more of the error rates that you see in one physical qubit. And so that's sort of the biggest problem in itself, is dealing with the noise, and two, just the sheer volume of control that has to happen. And it's all RF based control, so it's all radio frequency based, like microwave type control signals that are going through this. So you've got the fridge itself has to be able to take in all these wires, and then the heat that's generated out of that. That's all another consideration. There's a lot that has to work, and all at nanoscale for all of that for them all to work together.
That answers the question. Oh, there's another question here. I will pass it on if case
It's a comment rather than a question. I thought quantum computing is rather like nuclear fusion. That is, it'll work in 20 years' time, but that 20 is a constant, doesn't decrease as time goes on.
Did people hear that? Yeah, the idea that it'll work in 20 years' time, but it always remains 20 years away. Yeah.
Something out there already.
So did you hear that? So is quantum computing allowing you to do things already? And I think the answer is yes, because we've seen artworks.
Yeah. Yeah. So I mean, in terms of the most near-term problems that it's solving at the moment is in chemical modeling, chemistry. There's a few companies that have been able to do quite a few advances in batteries. I know car companies are using it for similar modeling, to try and sort of shrink that development time. They've been able to do things that that used to take 25 years to would have taken that 250 years to realize, and they did it in 3 months. That level of kind of speed up but these are very small on the scale of what quantum could do. These are very small systems that are sort of using a hybrid between classical and some quantum stuff to sort of break the problem up into smaller quantum sections kind of thing, where they can get some speed up even though it's a noisy system. And it's a small system, so there's been definitely some advances there. We're just not at the point where we have this, you know, this universal kind of quantum computer that can kind of solve for everything that we're trying to do. We have to break it up into its bits at the moment.
So can I respond too? So your skepticism might be right, Matt, but this is the United Nations have designated this year as the year of quantum because it's the 100th anniversary of the moving intellectually into that domain. And I think it's right to say that we're now in a position where we can grasp it intellectually. So we are moving forward conceptually in ways that more and more of us can begin to grasp. And that's what we as artists are trying to wrestle with. And so I think that the intellectual benefits from computing, rather in the line of Brian's question and my answer to that, is that we are there and we are able to move forward now, only recently really, but we are now moving forward and we will, more quickly than this 20 years, which may be X years, where X is an unknown quantity, of course.
Great. Okay. Thank you. So, David.
Just very briefly.
So I'm going to have to pass this on just in case.
Does the qubit always manipulate an electron, or can it manipulate other time particles?
Okay, so does the qubit always manipulate an electron, or can it manipulate other sorts of particles?
Yeah, there's a few different types. So electrons or photons or a few other. There seems to be there's about, I'd have to look up the other ones, but there's about there's like a number of ways that you can take advantage of that quantum mechanics in different things. Yeah, photons and electrons are two of the main ones.
I said a bit of a maybe a dumb question. Electrons are very small. Why are quantum computers so big?
Yeah, because of the cooling. They so to get the system down to be able to cool something down to millikelvin, so the electrons stop moving enough for you to manipulate them. That big giant dilution fridge, the part of that that's actually cooled to a millikelvin is about the size of my fist, and so all this power goes into making that millikelvin, and it uses helium-3 as well, which is extremely expensive. There's a lot of so just to get to that, there's that tiny amount of space to that. But luckily, for us, that electrons are very small, so we only need a small space to fit a lot of them in. So, as pros and cons.
Well, I've revealed my quantum physics knowledge there. Electrons are very small. David?
In the 1970s, there was a ternary computer built. How does this differ from the ternary?
Okay, so David was saying that in the 70s, I think it was in Russia, there was a ternary computer, so 3 states rather than 2. How is this different? Well, I guess in scale.
What was that? Sorry, 3 states.
The question really is: is there a connection between experiments with ternary computers and 3-state computers and quantum?
I mean, we've done experimentation modeling. Some quantum computing regimes had more than 2 states. It's just that was kind of like the easiest. 2 energy level systems was kind of the easiest way to kind of, the simplest way at the time to kind of think of quantum computing. But yeah, I mean, it can be any number of states, because overall superposition is just all possible permutations of that, anything between 0 and 1. So you could have 6, you could have 12, you could, and you know, it could, you know, conceivably you can have as many of those states as you want. It's just your problem's going to be error correction and noise. So you have to be able to manipulate this electron or manipulate this qubit in a way that you can get to those different points on the block sphere. Otherwise, yeah, you won't have a useful quantum computer. So it just makes it harder to do.
But just to answer your question theoretically, of course, that was dealing with 3-valued logic rather than 2-valued logic. But the sort of, and during the war, between the wars, there was a lot of interest in multiple valued logics, which moved into something which was actually the subject of my own PhD, was infinite valued logics, right? And an infinite valued logic, one variation of that is what's known as fuzzy logic, but that's a bit of a sidekick. Infinite valued logics have a theoretical relationship somewhat closer to qubits and quantum logic than 3-valued logic. Right?
Oh, there's another question at the back there. Yeah.
Sorry,
Again, I'll have to, unless you want to come to the front and ask your question, I will have to pass it on.
Yeah.
So I also have a problem with the word art. So the word art is also quite a, my understanding of mathematics is from Bertrand Russell, who is a contradictory character himself. He wanted to solve the mathematical equational solution, but he never really found the answer, from my understanding. So the word art, from my very old-fashioned understanding, it comes with a lot of emotion, ridiculously, and also pain, you know, like whatever you can think of. Like Schubert said, you call it Bach, which is very mathematical in his playing. I do play Bach as well. But Schubert once says that if you want to produce something that is art in one standard, you have to come through the pain of life. So how can that itself in itself is very already in our human life.
So
in order for art to take place. So what are that elsewhere that we're looking for via this new conceptual leap and practice? So that's my question.
okay, so
then answer to, I mean, how does it respond to some other people's understanding?
So Ernest would have heard the whole question. I don't know if people out there on Zoom would have. Really, it's a question about the term art and this relationship between art and mathematics.
And also like the pain in life. How can we quantify that into 1 and 0?
I don't know if art has to have pain, but I'll hand over to Ernest maybe because he heard the whole question. And
yeah. So the proposition is from our questioner. The proposition is that art has to be to do with going through emotions and pain and all this stuff, and then you get the art out of it, as if you can generate art from pain and strong emotion, right? That is, I have a word to describe my reaction to that. The word is rubbish. Sorry, I'm not trying to be offensive. I'm trying just as a because in fact you might go to a theatre and see a play which is all about anguish and people suffering, even dying, and so on. But if you go behind the stage and look at the playwright's work and look at the people doing the lighting, the actors rehearsing, the people making all the stage appropriate for the play, you'll find it's very, very organized, right? So the pain might be displayed in the art in some way, but the making of the art that displays it is often extremely rigorously done, often using mathematics or measurements and so on and so forth.
Risk and assessment.
Yeah, so it doesn't, it's a false notion to think that if I'm really suffering, I can make great art because I'm suffering. That isn't how I make great art. So I think if you listen to Bach, you can get a lot of emotion from that music. But he made it using mathematical concepts. And he said he made those mathematical concepts in order to generate the harmonies for the glory of God, right? He actually said words to that effect. But that's how he did it, not how we react to it. So you have to differentiate between the experience that we get from art, from the making process of that art. And they're not mirrored. They're not mirrored. Well, I don't know about every single artist. There's some artists who think that they can take a lot of drugs and splash paint about and produce a great painting. But I don't think that they turn out to be very successful in that.
But the successful ones have some logical foundation.
So, I mean, for example, in painting, think of Jackson Pollock. Okay, if you look at a Jackson Pollock painting or a picture of him working, it seems like splashing paint about. But in fact, he was moving very carefully. And in fact, the physics of his body and the way he moved, okay, was almost like a dance, generating a painting from an organized way of choosing the paint, of holding the paint can, of moving his body, and so on. So that even though the work doesn't look as if it's organized mathematically, it isn't, but it comes from an organization, in his case, the movement of his body in a structured way that he thought about.
Thank you. I'm still alive.
Okay.
Okay, thank you very much. So just about at our hour and a half, almost 8 o'clock. There aren't any more questions. What I'd like to do is potentially just have a little chat with David Upton. David, like myself, is involved in the Computer Art Society, and he is continuing this exploration next year at an exhibition at the BCS Moorgate building in London. And I don't know, David, do you want to just say a little bit about what you have planned?
Yes, it's a strange feeling, really, almost a deja vu, because if you know anything about the founding of the original Computer Art Society, it happened just after the Cybernetic Serendipity exhibition in, I think, 1968. A lot of people got together. They became very, very interested in the possibilities that this exhibition revealed. But the problem was none of them had a computer, or those who did had a very primitive one. And people got together, those who were lucky enough to have a computer in their office would let their friends come and play with it. And it was just somewhere where you could talk to people about computing and explore the ideas with people who were similarly interested. And I think we're very much at the similar stage now with quantum computing. We've all heard of it. We all know all the jokes about quantums and things like that. But actually getting our hands on one is a difficult business. Jonathan said early on in this talk that in order to use quantum properly, we need to see things differently. I think that's right. And if you can find one set of people who are good at seeing things differently, it's visual artists. So I hope that we can help in that respect. So what we are trying to do in March the 17th next year, is to put together an evening which combines some of the theory, but really more from the practical point of view. Here I am, I'm an artist. I want to use quantum techniques or quantum ideas. Where do I go? What sort of things can I find? And we hope, for instance, that you will leave the exhibition or the Zoom with clear instructions as to how to actually set up a quantum simulator on your own system, and an actual quantum tool that you can use, sort of off the shelf, to help with your own art production. That's one of the things we've got planned.